So we finished with the probabilistic methods, and we can do with very simple linear model. You already know in the machine learning, or if you learn in the statistics or in the data mining, you may know about the linear classifiers or linear model. Yeah. Most learning methods aim to find the coefficient of a linear model. The linear model means I have x, or I have a feature, I have a variable, and I want to determine the y. I want to determine the target. Yeah. A simplified classifier with only 2 dimensions can be represented by a line. So for example, the line has the form wx1x, w1x1 plus w2x2 equals to b. So let's say this is the x1 and then this is the x2. So I want to know what will be the linear classifier. Let's say this is the line, then the black one is the relevant document and the white one is the non-relevant document. So x1 and x2 correspond to the factor representation of a document. The factor representation can be anything. For example, you already know until now, we can use the Boolean. It means 1, 0. Or we can use the count. The count means the frequency. How many words appears in documents. Or we can use the TF IDF. So there are some kind of real values or probabilities. How many times the word appears in the document with some ratio. So we can use the linear form and we can find the parameter W1, W2, and B. So those are the parameters that we need to learn, and the classification will be based on this formula. So W1 x1 plus W2 x2 higher than B, then yeah, we can make this kind of graph. If it is n-dimensional space, okay, so in this case we have only 2. If it is n-dimensional space, then W transform. This is a factor. Yeah, another factor will be equal to B. So this factor means we can have x1 until n, something like that. Yeah. So we can also use other linear classifier. What we learned previously was naive Bayes classifier using the probability. We can use the Rokio method, the one that we learned before, or yeah, some other method like Windrow-Hoff algorithm, support vector machine, and etc. So let's just make it very simple classifier like this one. Suppose we have this following data. So I have the word like what we saw before. The document 1. How many words of recommender? Okay, let's say 3. How many words of the word intelligence? 0. How many words of the word learning? There is 1. How many word school? Okay, 0. Okay, this is relevant. Document 2, we have this word. Okay, this is irrelevant. The document 3, this is the word and this is relevant. The document 4, this is the words and it is irrelevant. Okay, so we can use this one as the feature. Or if you want to convert this into TF-IDF, so this is the TF-IDF. Then we can know that, okay, the word recommender is high in the ratio. Maybe this word will be like the most important words to find the relevant document. So it is in the document 1, it is relevant. In the document 3, the word intelligent and the school, it is relevant. So later we will look at the Google Colab. Okay. So this is the result. When you use the classifier, you can distinguish with the line. So if you have n-dimensional space, you can have two-dimensional by using the PCA. So I don't explain about the PCA, but PCA is one of the method to reduce the dimension. When you reduce the dimension, let's say we want to reduce into 2. Then from 4 dimension, we reduce into 2 and we can make the linear line like this one, and we can distinguish which is the location of document 2, which is the position of document 3, which is the document 4, document 1. Because the document is too small, maybe yeah, it's not that relevant to find this linear. We can also use decision tree. If you learn the decision tree in the data mining, we have the decision tree for the recommendation problems. Inner nodes. Okay, we have inner nodes and we have the outer nodes. Okay, or sometimes we have we call it internal node and external node. The internal nodes, it is the nodes that still can be split. So this is internal node. This is internal node. External node, or sometimes we call it leaf. Sometimes we call it leaf. This is the end of the node. 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 Okay. So the inner nodes or the internal nodes labeled with the item features. So this is features. This is features. It is used to partition the test example, whether the word exists or not exists. So in the basic setting, only two class appears of the leaf node. Okay? Leaf node. Leaf node means the decision, whether it is relevant or not relevant, interesting or not interesting. So the decision tree can automatically be constructed from the training data. So if you have the training data, we can construct this decision tree. And it works best with small number of features. And yeah, you can use the meta features like author name, genre, yeah, instead of the TF, ITF representation. So for example, I have 4 documents. So the documents, one, we have the word recommender, intelligent recommender. So this is relevant document. The document 2, there's a word recommender and learning. This is relevant. The document 3 includes recommender, school and intelligent. This is relevant. The document 4 includes the word teacher, homework and science. It is irrelevant. So if I have this word, what will be the result? If I have this word, what will be the result? Okay. So I can have this table or this data and I can convert into table like this one. So in the document 1, I have the word recommender. Okay, so let's say this is the Boolean. Okay. I just use the Boolean factor. Boolean means 0, 1. Exists or not exists. In the document 1, the word recommender exists. The word intelligent exists. Okay, the label is 1. The document 2, the word recommender exists. The word learning exists. So the label is 1. The document 3, the recommender is 1, intelligent is 1, school is 1. Okay, label is 1. For the document form, the word teacher, homework, science, 1, and the label is 0. Now, let's say with this data, I got this decision tree. So this decision tree is a result from this training data. We call this is the training data. And we want to have a new data or something that we want to predict. And if I have the word recommender, teacher, and homework, recommender, teacher, and homework, what will be the label? Let's check this one. Is there any word recommender? Yes, because there is a word recommender. Then let's check to this one, intelligent. Is there any word intelligent? No. And we go to this one. Is there any word learning? No. And it goes to here. Then what is the label? Oh, it is 0. Okay. This is irrelevant. Sorry. This one 0. Based on this decision tree. Now let's check the teacher and science. The teacher and science, we have the word teacher. Science. Is there any word recommender? No, there's no word recommender. Then it goes directly to irrelevant. So the predicted is irrelevant. Okay. So this is the decision tree that is the model that we can use to do the prediction. Yeah, there will be some improvement for this prediction. The process of choosing a subset of available terms. So if there are many terms, you will have difficulties. So we can just choose a subset of available terms. If we have like 1,000 terms, okay, we can reduce only 100 maybe. So if you can reduce this one, then it will be easier for you to do the prediction. Different strategies exist for deciding which features to use. So feature selection based on the domain knowledge and lexical information from WordNet. So if we use this kind of content-based recommendation system, usually we use mostly related to the text representation. If we have the domain knowledge, if we use the WordNet, then it will improve the feature selection. Or we can use the frequency-based feature selection to remove words that appearing too rare or too often. So it means we have X, so the word is X, and then we set a minimum and we set the maximum. So if the word is too rare means very less. If the word is too often, it means high frequent. So we will cut it. So we do not want, we want only the word that is the common frequency, in the common frequency. So the feature selection, it is not appropriate for larger text corpora, means if there are so many words here, it is impossible. Like, in the chat GPT, nowadays, I think it goes to 13 billion parameters. 13 billion parameters. So you can imagine how big is the parameter. And yeah, if you use all the parameters, Yeah, it depends on your computer. If your computer is strong, then you can do this one. But if your computer is not strong, yeah, you cannot do this one. So it is better to evaluate value of individual features independently or construct a rank list of good keywords. So sometimes we need to define like the predefined keywords. So if we have the predefined keywords, we can remove some less important keywords. Or we can use some kind of way to determine the utility of the keywords. For example, the chi-square. Or we can use the mutual information measure or like the Fisher discrimination index. For example, using the chi-square. The chi-square, it will show you the correlation. For example, how many times the term T appears. So this is a number. And if the term T appear in the class relevant, we have A. The term T missing in the class relevant, then we have B. If the class irrelevant, if the term T appear, we have C, and we have the term T missing, we have T. So you can calculate by this formula. So A represent the number here, B represent this number, C represent this number, D represent this number, and A multiplied by D, and B multiplied by C, and then we do the square. Divided by the A plus B, A plus C, B plus D, and C plus D. So we have the chi-square. The higher value of chi-square indicate that the events of the term occurrence and the membership in the class are not independent. If it is not independent, then it means there is a high relationship between the term and the class. Okay, I guess you already learned the chi-square. I will just show you with this formula. So what are the limitations of the content-based recommendation model or the recommendation-based content-based recommendation methods? We usually use keywords. Keywords alone may not be sufficient to judge quality or relevance of the document or web pages because there might be some up-to-dateness. Up-to-dateness means sometimes people will make the updates of the website. For example, in our university, the web always be updated every year. So the relevant is meaningless when there is a new update. Usability. The keyword may not be usable in the web as many as the documents. For example, we know Hanguk is academic institution, but when you search on the web page, is there any word about academic in the website? Maybe the website maybe about the EPUB application, registration, exam, but there is no word academic. So sometimes the keyword may not be sufficient. Aesthetics. Aesthetic means just for the beauty of the documents or web page. For example, in the academic, it is relevant to find something related to accreditation. Accreditation. I don't know what is the Korean. It's like certification of the university. Yeah, this is for the aesthetic. If you want to search a good university, you need to check the accreditation. But actually, the word accreditation may be only one or two. This is for just aesthetic or to prove that the university is good. So the keyword is not sufficient. Or the writing style. If the writing style is very good, yeah, maybe the keyword is also very less. And the content may also be limited or too short. So if the keyword or the content is very short, I like the school. So it's very short. So it cannot represent the contents. Or the contents may not be automatically extractable multimedia. If you can use emoticon. Emoticon. So in Korea, I think in KakaoTalk, there are a lot of emoticon and you can say like debug in emoticon. But can you extract that one? It's still difficult because it is in the term of multimedia. So it is not easy to extract that content. And also we have some things related to the ramp up phase required. Ramp up phase means, if we have some training data, it is good. Yeah. But if we have like this word, web 2.0. So nowadays there are so many words like industry 4.0. And then sometimes people put industry 5.0. So people keep improving with this word and it is not easy to use this as the content. Or there might be some over specialization. Over specialization means the algorithms tend to propose more of the same. More of the same means, we just use the algorithm only for specific domain, maybe only for movie. But when you put the data from books, it is not relevant. Or two similar news items. So if you put only the data with only related to sports, so if you have a lot of sports data and you want to classify sports and entertainment, then it is also not relevant. So there are so many limitations, and I guess you can find one of the limitation and you can try to cover it in your team project maybe. Okay, so the things in this content-based recommendation, it is contrast to the collaborative filtering approach. In contrast to collaborative approach, content-based techniques do not require user community in order to work. What does it mean, user community? So we don't need the rating. We just need the description. The description of the movie, the description of the books, or the description of the items. Okay. So that can be used to make the recommendation. And the presented approach aims to learn a model of user interests, preferences based on the explicit or implicit feedback. So if we have the feedback, if we have the rating, then it is additional information. And this additional information can be used to look at whether this is relevant or not relevant document, whether this is the item that user like or not. Deriving implicit feedback from user behavior can be problematic. Okay? And evaluation show that a good recommendation accuracy can be achieved with the help of machine learning techniques. Okay, so we learn about this one. This technique do not require a user community. It's still the same. You can put the documents with the relevant terms using the TF-IDF or using the count and etc. Danger exists that recommendation lists contain too many similar items. So all learning techniques require a certain amount of training data, and some learning methods tend to overfit the training data. So this is the problem of overfitting. Or we have what we call as imbalance problem. So overfitting means the data of the training is very good. The training is very good, but it fails on the testing data. Imbalance problem. The label is dominant in one class. So the class one is many, but the class zero is this. So we have the imbalance problem. And yeah, this is the things. Okay. Pure content-based system are rarely found in a commercial environment. So usually people will use the content-based and the collaborative at the same time. Let's go to the Google Colab before I finish the class. This is just a simple So this is a simple code that I give to you. Okay. Let's say we have the movie A, movie B, movie C, movie D, and movie E. And we already have the genre. The genre is action and adventure for movie A, romance and drama for movie B, and action and thriller for movie C, drama and romance for movie D, and adventure and fantasy for movie E. So we can create the data frame. Let me make it very simple. So we can use the TF-IDF. So the TF-IDF, it's already available in the sklearn. So you can just use it. And once you create the TF-IDF matrix, so you can look at this one, F-IDF matrix. This is matrix that it is already stored in the memory. Okay, so you can use the cosine similarity. So the cosine similarity is to check whether the documents and the keywords we want to know which are the most similar. Okay, and we can make the simple recommendation based on the similarity measures, and we can sort based on the highest similarity. So let's say I want to know what would be the recommendation if I have the movie A. Okay. So I know the movie A. The movie A is about action and adventure. So can I recommend another similar movie with the same content, with the similar content? So if we look at this data, maybe the movie C, because it is the same action, and movie E, because it is the same in the adventure, and the other movie is not that relevant. So the most similar is action and adventure. Then if I look at the result, the recommendation for movie A is movie C, okay, movie E, movie B. Why? Why movie B appears? Movie B is romance and drama. Meanwhile, movie C is action and movie E is adventure. Okay, this is irrelevant. But movie B, why it appears? So later you can see this similarity score. Okay. So we sort the similarity score and we just want to get the top three similar movies. The top three similar movie means yeah, any movie which is in the rank 1, 2, and 3. So it will show rank 1, 2, and 3. Even though it is not relevant, but it is still in the list. Okay? Because we have only five movies. So the recommender will always show four movies. And yeah, this is the one that I already show you in the class about the recommender learning and so on. So I show you with the linear regression. Yeah, you can take a look on the details. I use the PCA to reduce the dimension. And let me just create this one. So this is the linear classifier to show which is the position of the document related to the particular terms when we have this linear model. Okay, that's all that we can learn. Any questions, comments?